Hey all, welcome. Today is another day of a update for Hypermesh Lattice Mesher. Let's jump into it. This will be rather a quick one. I will go over the changes. So basically, the change I have implemented yet is the updating process of materials. Well, yeah. Let's first jump into the Git tree. So you see, I'm on a branch called feature sort 1D elements, which is mainly what I'm doing right now. Or you also could also just quickly go here. So yeah, so I'm on this branch. I will do a pull request shortly, and yeah, we will be going over the changes. So yeah, let's get my Git graph here. Not really sure what was the last one, but the main is here. So I think those steps are new. But the current one is yeah, the most, has the most content, so I will focus on that. But I will show everything, so don't think you have to walk the Git graph to just understand what I'm telling you. You should be fair if you just have watched the last video. But alright, so what I did, I created a new command. So the last two videos, I guess, were about the Hyperview scripting, right? So we had methods which could then export like displacement stress values from our run models. And then was the question, well, we get something like this, data values output dot text. Yeah, so something like this. You have a ID and you have a value. So this could be anything, but it's not properly named. But yeah, it's in this case stress values. So for every element, and in this case we're talking about rod elements. Maybe I should show that to you in a minute. Let's just start up Hypermesh. So we have for each rod element, we have a stress value, rod stress, axial stress, right? And now we want to change, for example, material parameters on that metric. So how to do this? We have a new command here, and this started with me calling that create materials, because the first thing what I did, and I also streamed that on Twitch. Yeah, I just experimented a little bit with Twitch, so I don't know if you're interested in that, but yeah, I have a Twitch channel. It's pretty in the early stages, but yeah, maybe sometimes we will get to see each other there. I would be pleased. Yeah, so we have create materials. That was the first name of the instance here, and what this was doing in the beginning was just to create a bunch of materials, because the thinking was like, you could go for one approach, just assigning a material for each and every element in there. But this will get a rather large amount of materials, so you don't want that. You want a finite number of elements, no, a finite number of materials where you could assign your elements to. So let's just imagine you have a bunch of elements, right? I will just load a, wait a second. We'll just load a finite element model here. Here. I also included the test files for future tests, because shame on me, I have not implemented the tests yet, but yeah, I will do that in the future. So we have a model like this, right? So lattice rod structure. And now we have in this model, if you go to the model tree, there's one property. Now you could go and just depending on the stress value for each element, create a new material, assign that, whatever. Not good. So what I did instead was just be able to create a bunch of materials, like for example 10. Then you have 10 baskets. And now you have to do a mapping. And let me just quickly draw that for you. If you have, for example, a range from here to here where you have your sets of materials. Let's be fair, we have just 4 equally spaced materials with different properties, and what we are changing here is the Young's module. So we have a low Young's module over here, and we have a high Young's module over there. But the values are of unknown range to us. So you don't really know what you're dealing with. So you could end up like with minus 1k, for example, with stresses. That's possible. You could also have here maybe just 250. So you have an arbitrary range. So what you do is you just take this number of elements, or I'm always getting this wrong. I'm sorry about that. You have a number of materials, and you're taking the number of materials and do just equal steps here. And then you just see, you look at an element, and the element has, for example, like 150 MPa of stress value. Well, then most likely it will belong into this category, right? Because you can see where it lies. Actually, I'm not quite sure if that is minus 1k. I'm not sure if that's right. But, all right. Actually, I made everything absolute. And so here would be a 0. And then most likely it would be here, right? Or here. Whatever. You know what I mean? So you're just making a... put the element into the right basket, right? So this is the thing what the code is doing. All right, so now let's look at the code and just walk you through there. So it asks you for a path to the 3D FEM file. This is the finite element method file where your lattice structures are in, and you have run that file, and you have analyzed that file with a command like the read stress command up here, right? So we have that. And the second one, the second parameter here, is the path criteria. And yeah, I should put that into the doc string later. But yeah, so if you have 2 file paths. Now, I have default ones for my model testing. And if that's not the case, it's just going to replace backslashes with slashes because Hypermesh doesn't like that. And I see there's a mistake here because I have not made it parametric that you could define a number of materials, Young's module. Yeah, we could maybe just put it in something like material info, and this is a tuple. And this contains, should list that here. This is a tuple. No, I'm not sure we need to have 3 values. We can have tuples inside tuples, right? So let's make it a tuple. This is like number of materials. So how many materials you want to create. And then we have another tuple inside the tuple, which is min Young's module and max Young's module. Hopefully that's understandable. If that's not quite easy enough, I can also write that. Info containing the number of materials to be created, as well as lower and upper constraints for the Young's module. So I think that should be fair. All right, so this is out of the way, and then we have this, and this is not accessed here. Why is this tuple is not defined? Why? Should be here. It is not. All right, so we have that, and now, so Young's module would be material info 1. Well, actually, that's not really how it works, right? Let's make it like this. I think this should work. So I unpack the tuple, which is a tuple inside of a tuple, which has also a integer as the number of materials. I think that's okay. So I have then the number of materials to be created and the Young's module with it, which are the lower and upper bounds. So this will then trigger this method here, which I put inside the material class, create materials. So this just creates a bunch of materials, and I think I have tests for that. So this I had done. So and this just does something with a delta, which is just upper minus lower of your Young's modules. Well, both have to be positive in this case, right? But just make sure that, yeah, just make that an absolute values. And yeah, now we have the problem that upper always has to be more than lower, but yeah, don't care about that right now. So float number of materials -1. Why did I do that? If you have just 2 materials, you want the delta to be the whole thing. And that's why if you want to have 3 materials, then the delta should be half of it, right? 3 -1 is 2. So delta is the actual delta divided by 2. Yeah, makes sense. So you have a delta. This is the step size from material to material. And then for I in range of the number of materials, you just go up and create the materials and assign the linear properties to it. So this is fairly easy. So you create the materials, and what this method also does, it returns your materials as a list, so you can work with it. And then for sure you have to create that in a TCL script file as well. So you create TCL commands for creating all those materials and properties, which is done in this method. So this is rather boring to go through there, but it's just creating the materials and the properties with same naming convention as before. So it's like material underscore and then the ID, or mat, yeah, mat underscore ID. Same thing for property, but I think there's property and not prop. That's actually important that this is the same as later, because in later stages we will need those to be in this way, because we need to reference those infos, right? All right, so a little bit hectic. I apologize for that, but yeah. So you have this command, and then going back, you just write your TCL script section which creates the materials, creates also the properties. Then it imports the FEM file which contains your lattice structures. Having this in the file, you can then assign the elements to new properties, because you created the properties with the materials. No components, by the way, no components, because you have the properties and the beam sections are directly mapped to the elements. There's no components whatsoever. So properties assigning could be taking place, but you have to do the mapping. So the mapping is done here. Element ID to property name. And actually that has changed. You know, what I did at first sight, I just thought, well, for sure, just go through the list. You have the list here, like this. And you just go for every element ID. You assign you do a mapping. Which material should I choose? You do this thing I showed you here. You just get the ID of the material you want to put in there. So you get the property name, so you could assign it. But the thing is, you will end up with a huge file which just contains those multitude of assignments, like create a mark of one element, assign a property to this element, and then you're doing that for the next element. Next element, next element, next element. It's n complex, but it's unnecessary, because what you also could do, just flip it around. What do I mean by that? So you just do, instead of element ID to property, you do property ID, property name to element IDs. You just get all the element IDs which have the same property, then you have as much assignments as you have materials or properties, respectively. So this is a better way of doing that, and I first implemented the obvious solution, which is element to property ID or element to property name, and then thought about it and get it differently. And I think this is far better, but it's still not optimal, because I thought, well, there's something similar happening as in the first stages, where I just put in the FEM file with TCL commands, you could also definitely update the properties on the FEM file itself. But I think I will move that onto a later stage, but because I think there's a little bit more complexity to it. And I think it's running quite smoothly until now for the easy model. So I will not bother for the meantime, but it's in the back of my head somewhere. All right. So we have property name to element IDs, and this is actually the main method here. Fetch element ID to prop name. This is doing the mapping, and you're giving a path to the criteria file and also the number, the list of materials. And what this is doing, this is this method. It's just creating empty dictionaries and just scans through that file and lists element ID to value. What it also gets is min and max values. And so it has the possibility to calculate the step size, because as you saw here, this is clear. This is just one index. And you have your Young's module, whatever. You have maybe 20K here as a Young's module and 40K here. So the step size is 20K and will go linearly to the next one. But here it's a completely different beast because you don't know yet the step size. So you're having the max value, you're having the min value. You just divide that section, this delta, by the number of materials. Then you have this step size, and then you can do the following, that you just divide the value. You take whatever value you have and subtract the minimum of it so that you have exactly this distance, and you divide this length by the number of steps. So, and this is an integer division, so this would be 1, and so you know the index is 1. And then you go into the list of materials and pick up index 1, and this is it. So a little bit slower. Again, you have the step size, which is max value minus min value, so this is the delta, divided by the length of materials. And I want to be sure that it's not an integer division, because you could have really small values here. So you don't want to have that a 1, and actually it would be a 0.001 value. So you're making sure that it is not a integer division. And then you iterate through the dictionary, having the element IDs and whatever is the value. Yeah, the value is the stress value. And then you get your ID for the material. And this is where the magic happens. You get the absolute, because I worked with absolute values. You get the absolute value. Then you subtract the minimum value, which is just the distance from minimum to the point of interest. So here, that's the value where you currently want to sort that in. So you have this distance and divide it by the step size. And so you get a, I'm not sure if that's a floating division, could be. So I round it to be an integer division, so I have an ID here. And then what also could happen if you have 250, which is the max value, the step size would be 4. But 4, 3 is max for the index. So you know 1, 2, 3, 4 materials, but index-wise this is 3 because it starts as 0. What you have here is if you have the idea material is equal to the length of materials, then you just subtract by 1. This is not perfect, it's not beautiful, but it works. It works. And then you can build your property name because you have the ID of the material this element belongs to, and then you can just make this happen, that you look into the dictionary where you have property name to element IDs, and you get the element IDs, or if there are element IDs at all. If there aren't, you just simply put in a empty list with, not really empty, but with the first ID of the element you want to put in. But if there are a list already there, you can just get that list of elements. This is temp in this case, and then you append the ID of the element you want to apply to this list in there. Then you set the property name, the key value property name, and the the value in the dictionary set to the new list where the element was added to. And then at the end you just return the dictionary, which is done here. And then you have just more TCL commands. So you write the TCL update thing here, which just iterates through the property name to element lists and then creates marks for all the elements and then does this rot update and assigns a new property. So this is that, and then we have just save model and you start your procedure and that's it. So let's look at a script, how this looks like. So you have data scripts, I think I called that model 1. So you have here, with 10 materials, you have something like this, right? So this is it. Now, let's see that in action. And I think maybe I screwed that a little bit up with the new tuples here. Because I want this to be able to be none. Because if I'm just testing, then I want default values. So then I do something like this. If that is none, material info equals, and then I will just put some values. 20,000, 120,000, and oh, that's the second tuple. And how many materials? Let's go with 10 again. So this should work. Is this 200,000? 20,000, yeah. Alright, something is not really working. Ah, comma's missing. So let's hope this works. Formatting issues. Let's open up a terminal. Whatever, what has it? Too many blank lines. Yeah, it would be helpful if you could format it, my friend. Okay, I got a terminal, and not quite sure if I should. Yeah, let's better do a task lint first, because the lint is always getting to your face and tells you what is wrong. And so I better want to just be sure that I didn't miss anything obvious before running the code. So linting is always a good idea to do that. So this is okay. I don't have tests yet. This would be my second option here then to run all the tests, but no tests are there for this particular method. So I can run a poetry shell, shell, and then Python -m, then my directory, and then main, and then update. What was it? Update material values. The CLI does always do dashes instead of underscores. And then I have nothing, nothing, and none. Hopefully this works. This does not work. Tuple index out of range. What? Can a tuple be none at all? Well, tuple index out of range. Let's just give an empty tuple. Is that possible? Should be, right? Empty tuple. Yeah. Not sure if that works, but yeah, we will try that. So instead of calling for a none method, okay, I think I could do something like this. But actually, in this case, that would be better if I just have something like this. Right? Because I have a tuple at the second place. Let's see if that works. I'm not sure why this is not expecting colon. You have a colon there. Uh, Not sure how to do this. I kind of don't like this thing. I could do something like this. That if it's initialized with 0 values, but it doesn't feel right, does it? Does it? But yeah, for the trick, I will search for a better solution. I'm sorry about that. I will just go with that. And again, tuple index out of range. But why? Well, then I think we just have to go with separate options. I think that's the safest. If number of materials equals 0, number of materials equals 10. If, yeah, lower young equals 0, lower young equals 20k. If upper young equals 0, upper young equals 120k. Right, so we have separate values and we can make just this thing here. But I think, the linter, I'm afraid for the linter because the linter will say, oh, too many values. I don't like it, I don't like it at all. Well, I have to search for a better solution. I don't care about the linter right now. Number of materials is an int. Lower young is also could be a double, could be a float. Upper young also a float. All right, and then this is gone, and this would be a new job tuple, lower young and upper young. What did I just see here with lower upper young? The lower upper young is not anymore there, is it? No. All right, then let's do that again. In this case, it will be 0, 0, 0. Yeah, there's some oddly print statements in here, to be fair. If that runs now correctly, yeah, this should seem to do the trick. I can just, not those, but I can just get rid of those values. Let's see one more. There's still some print commands in here. Yeah. Debugger on its way. Wait. Still. No. It's just me being lazy, didn't save it, right? Yeah. So this comes from the create materials that was just for testing purposes. Yeah. But I will deal with that later. So you don't have to bother with me to go through there. All right. Yeah. So this is it about it. Yeah. I mean, I will just commit those two to be a hotfix. What did we do? Made CLI a little bit better. Yeah. Quick fixes. All right. What's next? To be fair, I don't know really. I think the next things should be then to have some testing models. I mean, there's a lot of to-dos, to be fair. So if you just go in here and go to the issues, you will see that there are some issues. And also, I think there's some work to do for the student group to just be able to implement own lattice structures. or stuff like that, which I did not focus on. And also this optimization procedure you could do now because you have a way to update the material properties. I mean, the basics are there yet. I think, yeah, there's still much to do. All right. Yeah. Thanks for watching. Thanks for being here, staying this long through the code, and also, yeah, through the little mistakes here and there. I screw up from time to time, so, but I think that's normal. So I won't mock myself for that. But yeah, I just apologize for you having to see some of that shining through. But on the flip side of that, it's also good that you also see it's just, yeah, it's just ordinary work. It's just things go wrong sometimes, and then you have to push harder and try to figure it out. So that's just normal, I guess. Yeah, thanks for watching again. If you like it, subscribe, hit the bell, you know what to do, and leave a comment if I can help you in any way, or you have suggestions, also possible. If you want to contribute to the code, I'm open for all of those kind of things. So yeah, have a great day, evening, whatever it is for you, and take care. Goodbye, guys.